Is it possible to find a single mathematical equation capable of completely neutralizing a complex spatial transformation? To answer that, we turn to the definitive text on the subject, Hoffman and Kunze's linear algebra. This is the exact environment where students first confront the rigorous limits of abstract vector spaces. In basic algebra, a standard polynomial is a machine. You plug in a scalar number as a variable, and it outputs another number. We can perform a conceptual leap by replacing the scalar variable x with a linear operator t. To maintain algebraic consistency, the constant term adapts to the operator logic by multiplying against the identity matrix. Evaluating this polynomial generates a completely new linear operator, built out of scaled powers of t. Our search is focused on finding an equation that drives this entire configuration to zero, an annihilating polynomial. In this framework, polynomials act as algebraic machines capable of processing and neutralizing spatial transformations. The formal definition is straightforward. An annihilating polynomial is any polynomial p such that p of t equals the zero operator. This bold zero represents a matrix, not a scalar. The zero operator maps every possible vector in the space directly to the origin. Finding an equation that destroys the operator serves a practical diagnostic purpose. Forcing an operator to yield a zero result reveals its absolute structural constraints. These constraints expose the hidden architecture of the vector space, such as its invariant subspaces. Identifying an annihilating polynomial allows us to decompose complex vector spaces into simpler t-invariant pieces using pure algebra. To make the math computable, we shift from abstract linear operators to concrete n-by-n matrices. This raises a question of existence. How do we know an annihilating polynomial exists for every matrix? We find the answer in the dimensions of the matrix space itself. The space containing all n-by-n matrices has a finite dimension of exactly n squared. If we track the sequence of the powers of matrix A, the identity, A squared, and so on, they populate this bounded space. We can continue this sequence all the way up to the power of n squared. Counting the terms in the sequence from the identity matrix up to a to the n squared yields exactly n squared plus 1 terms. Because the space only has n squared dimensions, this collection of n squared plus 1 matrices cannot be linearly independent. Since they are linearly dependent, some non-trivial combination of these powers must sum to the zero matrix. These dimensional limits guarantee that every finite matrix eventually loops back on itself, forging its own annihilating polynomial. While that proves existence, manually calculating n squared plus 1 powers to find the dependency equation is computationally inefficient. Arthur Cayley identified a more direct route to finding this polynomial. Working with William Rowan Hamilton, he formalized a shortcut known as the Cayley-Hamilton theorem. The theorem states that every matrix satisfies its own characteristic equation. This means the characteristic polynomial, the determinant of xi minus a, is always a valid annihilating polynomial. However, the characteristic polynomial often contains redundant factors. To find the simplest working equation, we use the minimal polynomial. The minimal polynomial is the unique monic polynomial of the absolute lowest degree that annihilates the operator. While Cayley-Hamilton provides a universal fallback, the minimal polynomial provides the most efficient algebraic description of the operator's constraints. We can see the minimal polynomial in action through a concrete example from Hoffman and Kunze. This is a specific 4x4 rational matrix, designated in the text as matrix A. We begin by computing its successive powers to identify where the linear dependency occurs. Multiplying the matrix by itself gives us A squared. Note the numerical pattern. 2's now populate the corners and the center of the grid. Multiplying by A again yields A cubed. Matrix A cubed repeats the structure of our original matrix, but every non-zero entry has been scaled by 4. This reveals the linear relation, A cubed equals 4A. Subtracting 4A sets the equation equal to the zero matrix. This matrix relation corresponds directly to a polynomial format. Through matrix multiplication, we have identified the minimal annihilating polynomial for A. P of x equals x cubed minus 4x. We can factor this polynomial into x times x minus 2 times x plus 2. As demonstrated in Theorem 3, the roots of this minimal polynomial, 0, 2 and -2 are the exact eigenvalues of the original 4x4 matrix. This confirms the link between abstract spatial transformations and algebraic equations. Every finite-dimensional operator is mathematically bound to have an annihilating polynomial. The characteristic polynomial provides a universal starting point, while the minimal polynomial identifies the most efficient constraint. These polynomials define the set of characteristic values, the spectrum, of the linear transformation. By defining these roots, annihilating polynomials dictate how the operator scales its characteristic vectors and reveal the fundamental limits of the transformation. Subscribe for more rigorous breakdowns of linear algebra and the works of Hoffman and Kunze.